All right, good afternoon, everyone. My name is Alan Meadows. I'm a lead cloud architect for AT&T.
I'm Rodolfo Pacheco. I'm also a lead cloud architect for AT&T.
And I'm Seung-Gyu Han. I'm from SKT. I'm a senior cloud architect.
And today we're going to be talking about Airship, making lifecycle management for open infrastructure repeatable and predictable. So the agenda for today, first off, is what is Airship? Second to that, the sub-projects that compose Airship. And then following that, we're going to review what an Airship under cloud looks like. And then Rodolfo is going to walk us through a series of animations to describe how Airship actually works under the hood. And then finally, we're going to talk about project adoption, and SK is going to give us an update there. So what is Airship? So Airship is a collection of interoperable and loosely coupled and, of course, nautically themed open source tools that provide for automated cloud provisioning and lifecycle management in a completely declarative and predictable way. Those last two words, declarative and predictable, are really foundational to this project. I'll take it a little bit further. At the core of what we're delivering with Airship is a unified and cloud-native way for us to manage containerized software delivery of cloud infrastructure services. All of the Airship components help us manage sites from their creation to minor updates through configuration changes, and finally major software uplifts such as OpenStack upgrades. The focus of the project has been on the implementation of a declarative platform to introduce OpenStack on Kubernetes and the lifecycle management of that resulting cloud. I like to say, simply put, the goal is to take baremetal infrastructure from data center loading dock to a functioning OpenStack cloud and then care for it beyond. Really, we're talking about a complete end-to-end solution without any requirements for operators to stitch additional tooling. And finally, Airship and all of its subcomponents are now officially part of the OpenStack Foundation. This is a fairly recent move that we just kicked off. We're really excited about the prospect of getting more people involved in the community. So I think the next question is, why Airship? So there's a number of tools out there that already deploy OpenStack, that provision operating systems on baremetal hosts, that do configuration management. The first logical question, I think, is why do we feel it was necessary to create Airship? So in order to answer that question, let's cover several key points of Airship and why it fits so well into the future GitOps approaches that we see evolving. So first, our site's definitions should be completely declarative. We want to treat both our declaration for hard assets that we want to materialize in a site, such as network configuration and bare metal hosts, right alongside the soft assets that define software, the versions to deploy, and their configurations in one full site definition. Our expectation is that we simply manage these YAML documents and submit them to the site where they're treated idempotently and realized by software. Users don't need to necessarily be aware of what's changed in the YAML documents. We submit the full document bundle every time, and we let Airship figure it out, whether that's an initial site deployment or a simple update to the existing site. The second is that we want to make containers our new unit of software delivery. We wanted to deliver software in exactly the same way, whether it was part of our own control plane or OpenStack itself, and containers are a key enabler for us to be able to do this. Containers also provide that required level of simultaneous coexistence and separation so that we can handle any number of isolated dependency requirements, as well as allowing us to progress containers that we release through development, testing, and finally production without changing them, so we know exactly what we're going to deploy every time. This gives us the ability to perform updates with absolute predictability. We don't need to rely on configuration management tools acting as release management tools operating within live environments, effectively leaving us guessing at whether they actually worked or not. We can also roll containers forward or back and leverage powerful orchestrators such as Kubernetes and Helm that give us things like orchestrated rolling upgrades and rollbacks out of the box. The third is that we wanted to ensure that we had a single workflow for all lifecycle management. What we mean by this is that we wanted to interact with the system in the exact same way, whether that was during initial site deployment or future upgrades in live sites. We use a unique process that we call Genesis, which we'll go into more, which forms a fully operational Kubernetes cluster containing all the Airship components on as little as one machine, allowing us to interact with the cluster during initial build-out the same way that we would deliver updates once it's fully built out with many hosts. Beyond that, we wanted to deliver updates to the system in the same way every time, so regardless of the change. So if you want to declare a new baremetal host that would ultimately get provisioned by Airship, make a configuration change to an OpenStack component, or completely change and upgrade the OpenStack version itself, you would do all of these in the exact same way. Update the site manifest YAML documents where appropriate to declare your new intended state, submit the whole site manifest to Airship, and it figures out the rest. Fourth and lastly, we wanted the platform to be flexible. So we wanted a single platform that could support very large cloud installations, small edge sites, different SDNs, all configuration driven. We don't want to have to modify Airship components in order to achieve these different configurations. We want it entirely configuration driven. And just as importantly, we wanted a platform that was flexible enough to allow us to manage more than just OpenStack. So OpenStack is a critical piece of containerized software that we deploy, but it is only one piece of a large set that we need to release and lifecycle in our control plane. And we wanted to manage all of those in the exact same declarative way. And finally, in terms of flexibility, we wanted to ensure that the intelligence was pushed to the edge as much as possible. What we mean by that is that Airship should not be a monolithic controller. By pushing the install, upgrade, and lifecycle rules into encapsulated things like Helm charts at the edge, this keeps Airship, and no pun intended, as light as possible and allows us to slot in completely new software with zero code changes. So what are the open source projects that Airship leverages or integrates with? So obviously, OpenStack Helm was an important integration for us. It's where we started with a lot of these concepts, and a lot of the exact same philosophies are in Airship itself. We use OpenStack Helm for two purposes. One is it's our mechanism for delivering an OpenStack cloud for our end users. And second, we use it to stand up the individual OpenStack services and infrastructure that Airship itself depends upon within the undercloud. Airship draws a lot from the OpenStack projects as well, which makes it a fitting place for the project to live. It uses them as standalone services to enhance the undercloud platform, but not in their traditional capacity to deploy virtual machines. Helm is obviously at the core of how resources within Kubernetes are managed inside Airship. And clearly, we leverage Kubernetes as our container orchestrator and gain all the advantages that that has to offer for rolling out updates, health checking, managing resiliency, and lifecycle management. Within OpenStack, Airship leverages Barbican for secret management and Keystone for authentication and RBAC within the Airship components themselves. We have future plans to integrate other OpenStack projects as well. One example is leveraging Ironic as a backend for DryDoc, declarative baremetal provisioning. Although DryDoc has a pluggable architecture, today there is no support for Ironic, but of course we can solve that. So what exactly is the Airship project composed of? First, there's Treasure Map, awesomely named. It's our documentation project outlining the various sub-projects and providing a reference architecture for the platform, things such as example end-to-end declarative configurations, Shipyard as the designated REST API front door for the platform, allowing, for instance, CI/CD systems to deliver YAML-based site designs and updates and operational actions. And Shipyard acts as the site orchestrator, leaning on the other undercloud components to implement the actual request. DryDoc is our declarative baremetal provisioning engine. Baremetal hosts are declared, including their network configuration, and DryDoc handles the provisioning, their operating system, BIOS and firmware updates, RAID configurations, and complex production network configurations. It works in conjunction with Promenade to label and join the host to a Kubernetes cluster. It was designed with a pluggable backend, so it can evolve to support provisioning infrastructure such as virtual machines, third-party clouds, and support other provisioning engines such as Ironic. Today, it supports Canonical's MAS as a service. Diving Bell is a Helm chart-driven, lightweight solution for bare metal configuration. So even though the intention is for us to containerize everything, there are still some elements of the operating system we must configure and manage going forward, and Diving Bell is our mechanism to do that. This allows us to treat even those kinds of updates like any other configuration-driven update. Deckhand acts as a centralized site design document storage backend. It keeps revision history of all site designs and changes, performs secret substitution so that we can separate out sensitive data, such as certificates and passwords, from traditional deployment data. And it allows us to layer documents so that we can reuse common site design settings across similar types of sites. This keeps YAMLs defining sites compact when there are elements reused or shared across deployments. Armada is our enterprise answer to orchestrating multiple Helm charts using a declarative YAML definition, allowing us to articulate every piece of software we will run in a site, where to pull those charts from, in what order they will be deployed, how we should group them, how we should test them, how we should roll them back if there's a failure, all in a set of documents that we can lifecycle. Birth is a minimalist virtual machine runner for Kubernetes, which may ultimately pivot to something else like KubeVirt or some other leading project in this area as they stabilize. Promenade allows users to deploy a resilient, production-grade Kubernetes cluster and provides us the ability to manage Kubernetes lifecycle using Helm charts. It supports our desire to manage installs and updates in the exact same way for every piece of software that we deploy, including Airship's own components, which run within Kubernetes themselves. Again, that uses a process that we call Genesis, and during Genesis, Promenade uses a single physical host to manufacture a resilient production-ready Kubernetes cluster, and all of the required undercloud components to start provisioning the rest of the physical environment, ensuring that we work with Airship components exactly the same way during site build-out as we would during an update. So obviously the resiliency aspect is only achieved when additional hosts are provisioned, but the point is that no further pivots or changes are required to actually achieve that other than adding the new hosts. So today, Promenade uses its own internal engine to manufacture the templates to bootstrap Kubernetes, but again, ideally we would love to transition the engine to kubeadmin or any other popular open source tool when it's checking all of those production, lifecycle, and resiliency checkboxes that we've identified. And finally, we've created Pegleg to help manage, build, and aggregate, validate, and test all of these YAML documents to help deployment engineers interact with Airship YAML document sets. So what does an Airship-built cloud look like? So Airship cares for almost everything that we see in this picture. Everything that we see in blue is an Airship project, and everything that we see in green is an open source project that Airship leverages to care for some aspect of the cloud. Starting at the bottom and working our way up, there's a bare metal host and a host operating system and network and storage configuration that is declared and laid down by DryDoc. Promenade handles effectively two aspects of Kubernetes management. The first is the manufacturing of the cluster and its lifecycle, and the second is that it handles Docker and kubelet configurations on new hosts, as well as joining them to the cluster and labeling them appropriately so they receive the right workloads. Airship instantiates Ceph and Calico, among other infrastructure, using Helm charts, all orchestrated by Armada, all within the undercloud to provide storage and network capabilities to Kubernetes. And all of the Airship components themselves are installed and maintained as Helm charts as well. And finally, OpenStack Helm is leveraged to provide a fully functioning OpenStack installation, as well as logging, monitoring, and alerting. The entire stack is installed and lifecycled the same, including Airship itself. So again, to sum it up, everything you see on the screen, almost every layer, is cared for by either Airship, by Airship for both installations and updates. So I'm going to turn it over to Rodolfo now to walk us through a few animations that should give everyone a clear idea how this is achieved.
So Alan's walked you through a lot of information. I'm going to give you a bit of a visual to help you get the information to sink in. The first animation is going to try to explain a little bit. We talk about declarative. There's a lot of documents. So what do we mean? What are we declaring exactly? Our cloud sites are defined by using a set of YAMLs. There's many that define our intentions for the site. These declaration documents describe the infrastructure, starting with the OS configuration detail, the network interface configuration, as well as other physical expectations for the bare metal servers. It also includes configuration for NFV high performance expectations, such as CPU pinning, NUMA, and other configurations. And for all the software being deployed, it includes configuration, version, image sources, as well as where the source comes from. This includes the definition for Kubernetes and Docker, Airship, the LMA stack, which is our login, management, monitoring, and alerting, as well as the OpenStack Helm components. Everything is declared, how it's configured, 100%. These YAML files are organized in a hierarchical structure defined by the Airship Armada project, where essentially we end up with one or more manifests comprised of chart groups, and each chart group is a set of independent charts. I'm going to walk you through how do we bootstrap the cloud. This is what Alan and what we refer to as a Genesis process, this idea of bringing up that first host on a data center or on a cloud site. This is the Airship Promenade-driven Genesis process bootstrapping the Genesis node of a site. There you see where we use Genesis to bootstrap what we call a Cloud Harbor site, which is a regional controller, if you will. In this case, we're running our CI/CD from this site. The site manifests for a particular site are fed into Promenade, and it will build a completely self-contained shell script that will be transported to the Genesis node. Again, those are all the documents we just talked about. We drive this through from a CI/CD location as well. In this case, the Genesis node is completely a vanilla node with an operating system installed. There you see coming up. There's nothing else at the OS. All the other artifacts will be instantiated by that Promenade-generated Genesis script. The site manifest documents are going to be used to generate a tailored Genesis script. And this script, when it's executed, will retrieve all the images from your image repository, wherever that happens to be. It will configure Docker and the kubelet. It will then utilize the Armada container to deploy Kubernetes, which itself has been defined as a set of charts. And following with the CNI, in our case, is Calico, the storage as a service, which is Ceph, the Helm server-side component, which is Tiller, and then we'll deploy all of the Airship components that Alan just went through. Deckhand, Docker, Armada, Promenade, Diving Bell, etc. And at this point, at the end of this, you're going to have a standalone Genesis host, Kubernetes standalone server with all of the Airship components ready to go, able to be interacted upon. So once we have that, the next step is we're ready to deploy a cloud. We're going to do that by leveraging APIs that are exposed through the Airship's Chipyard API engine. There is a special document we call the deployment strategy document, which provides a mechanism for defining groups of infrastructure, such as control plane servers and groups of compute. An example, we can group the compute servers per rack. In this document, we can dictate the sequence amongst the groups and what is the success criteria for each group. We're going to authenticate to interact with Chipyard. We're going to deliver the documents that we've edited and manifested. Chipyard then is going to try to, commit the documents. You can set the documents multiple times. When you commit, they will be validated. The relationship between the documents will be the reference, the structure, it's all validated. Once it's validated, we'll trigger the action to deploy, which will allow us to start building through dry dock the set of hosts that need to be, that are declared and we need to define. once a host comes up and is joined the Kubernetes cluster, Kubernetes will just normally schedule the intentions we have for that host. And dry dock will continue to do the same thing for the compute host. Again, following the strategy that depicted in the deployment strategy document. Once all the hosts are up, or at least are up with the success criteria that we've defined, Shipyard will interact with Armada, which will trigger the Armada manifest to deploy the software layer. At this point, we will be deploying the LMA stack, the logging, monitoring, alerting stack, as well as the OpenStack or the service layer stack that we call, which in this case is OpenStack Helm. And you see that as Armada is interacting with Tiller, who's interacting with the Kubernetes API, the different components of the stack will start coming up in the appropriate target places. And that's done by defining, labeling the servers, and you'll get the right services in the right servers. So here you see how Nova Compute, LibVirt, an example, are on the compute host. And in the control plane, you have the other OpenStack services. Now that's day one. What about day two? What happens when I want to update or extend the capacity or other changes on the cloud? Well, day two operations look pretty much the same as your day one. You're still going to go and have the ability to update the document set. Either you're updating the documents or you're changing configurations through updates, or you're going to add capacity by adding new documents. You can add new documents. You're adding a new service, or you're adding a new server, in example. After that, you're still leveraging the same APIs in Shipyard, the APIs to deliver the documents, to commit the documents, sorry, and to execute the transaction on the documents. Here we see how it's triggering. The only difference is you're triggering an update action through which you're going to deliver the documents. It's going to execute a workflow that is essentially equivalent or the same as the one that was executed during the deployment cycle. Shipyard, again, in this case, it went and talked to dry dock. In this example that is showing this animation, we're only updating some OpenStack service configuration. So dry dock doesn't have anything to do, but if it did, it would at that point interact with the servers. If you're in capacity, we'll deploy a server just the same way as we did during the deploy cycle. And as you see, it follows the exact same flow. Armada talks to Tiller, Tiller talks to Kubernetes, and it delivers the intentions that the documents have defined. In this case, we wanted to update Neutron, and we wanted to update the Nova Compute. And what you see here happening is a standard Kubernetes rolling update function being taken advantage of, which we do in this system. And that's an update. As you see, it looks the same conceptually as an update. One more animation. It has to do with, so we're talking about declarative. We're talking about a lot of documents. So we wanted to give you an idea of how we manage all those documents, and Alan made the point that we try to reduce the scope of the documents that define a site to be as minimal as possible. So we invented something called layering and some operations and YAML documents to facilitate that. So the declarative aspect of Airship implies there are many documents to manage per site. This, of course, scales with the amount of cloud regions being managed. We organize our documents in one or more repositories, and we define multiple layers, such in this case as a layer for global documents where we can specify the generic configuration for software artifacts, such as OpenStack Helm and Airship components. We can also specify profile documents that define hardware information, as well as host-specific configurations or security artifact documents. We also have this notion of a type layer. A type layer is, in example, if you have different type of deployments where you need to instantiate things in a slightly different way. Maybe your configuration it doesn't require the scale of another site. Maybe you have larger versus smaller sites, or edge versus non-edge regions. You can depict those variations at the type layer. It means every site that is following that criteria or that category can take advantage of those configurations as a once and done type of thing. Obviously, at the site level, you're going to have some information that's specific to the site. You cannot get around that, right? A bare metal server is going to have specific IP addresses and specific. However, you are specifying how I want to configure that server through those documents that we call host profiles. Tell me how to configure the server, or a hardware profile that I depicted at the global level perhaps is defining for me the model of a Dell or an HP or some other vendor's hardware once and that's it. So in the site, you also have a couple of documents that are special. There's one document we call the site deployment document that tells you which layers this site is interested in, what type of layer we care about. Am I an edge site? Am I a large site? And based on that, we built a tool called Peglet that document also has revisions and versions that the site is related to. So you can have a revision history, revision control, source control around the document structure. And that's depicted in the site. Peglet is a tool that we built to, based on that information, is able to gather the appropriate set of documents that are required for a particular site. Decant, our YAML server, provides validation infrastructure that we take advantage when Peglet is collecting the document to make sure that before you even deliver a document or attempt to deliver a document to the site, it's been validated, you remove as much possible, any possible errors that might exist in the documents. And now I'm going to pass it over to.
Okay, now I'm explaining how SKT used the Armada, expression Armada.
Is there one more slide? Yeah.
From the collaboration with AT&T with community, SKT is building Taco. Taco consists of OpenStack ham and Armada, SKT all-flash SAP, and SKT in-house tools, including analytics and operational automation tools. One of the benefits of Airship is that you can select sub-project you want to use and easily integrate with your existing pipeline. And in SKT, we use the Armada to orchestrate most of the control plane and operation tools to deploy OpenStack. Now I will describe details on how we use the Armada and especially in SKT in CI/CD pipeline. Basically, SKT uses the Armada manifest as a center of CI pipeline. We simplify CI pipeline with a single unified manifest and incorporate flexibility to do only necessary things per each change. For instance, when developers change something in value in Nova and push PR, Jenkins triggers job to launch Jenkins slave, and slave patches change the Armada manifest file and OpenStack chart, and the remotely call Armada API server in Kubernetes cluster to start deploying and testing what has been changed. In this stage, we use set option to only deploy Nova. What is better in this scenario is Armada will take care of any dependency to deploy Nova services, and since it is already predefined in manifest. In this way, its changes are testing only necessary part, but still maintain a single unified manifest that can be utilized in full deployment step. For CD pipeline, we are maintaining and versioning on Armada manifest for each deployment site. In this way, we don't need to change anything in OpenStack Helm chart to deploy different OpenStack. We just need to maintain a manifest per deployment site. SKT has several production deployments happening in this year and next year. For instance, first we SKT private cloud service, and second VDI service both for internal use and public, mainly targeting education service. And third one is for big data and analytics platform, and lastly for NFV infrastructure targeting 2019 greenfield production deployment. We will continue to collaboration in OpenStack community to enhance OpenStack Helm and Armada based on our production experience. And SK2 will keep upstream first policy both for Armada and OpenStack Helm. In addition, SK2 will start reviewing other projects in Airship for any feasibility to leverage and contribute more. We believe working together in this committee is always better than doing alone. Lastly, SK2 provides Taco-oriented script to deploy OpenStack with Armada. It's mostly very similar to we are using internally. So you will be able to do hands-on experience to use Armada and OpenStack Helm. So Alan, yeah, keep going. Yeah.
A little out of order slides here. So who are the contributors for Airship? So the Airship sub-project started in the open with the first line of code in active collaboration with the CNCF and OpenStack communities. And the ultimate goal is that the Airship projects are useful in and among themselves. For example, SKT just talked about their adoption of a single Airship project, Armada, to help manage and declare their complex Helm chart installations. So by making these projects independent as possible, scoped and good at what they do, we hope to garner contributions and adoptions, even if end users do not wish to take advantage of the entire stack. So who is contributing to Airship? So obviously AT&T for starters. This is essentially the foundation of our 5G core platform launch, what we're calling Network Cloud 1.0. We're already deploying using Airship today. The Linux Foundation Akrano project plans to leverage Airship for its undercloud deployment engine and is fully embracing the end-to-end declarative approach. In addition, SK leverages Airship as part of their Taco stack. There are also several companies evaluating Airship. So we're really excited about the transition that's happening right now, essentially getting the code into the OpenStack Foundation, and are optimistic that that will invite even further adoption and collaboration. So we're going to talk about how to get started. So where to go. So if there's one thing to take away from this talk, please bookmark this site. If anyone bookmarks anymore, airshipit.org. Try it out. So if you want to try out Airship, there's a project specifically for that. Again, remember, everything is nautically themed, so it's called Airship in a Bottle. With a single VM, you can launch the entire stack, including a functioning OpenStack installation that can provision its own VMs, and then you can kick the tires on the lifecycle management. And there's also a CI/CD status table up on the screen. The reason that this is worth highlighting is to show that these projects are real. They're in use. They have tests. They have significant coverage. They're far from vaporware. And the reason that we only highlight several projects here, which I think is important to point out, is that some of the projects are extremely simple, and this is enabled by the fact that the system is entirely Helm-driven. So this allows us to introduce projects like Diving Bell that we mentioned, and even Birth, as simple Helm charts with no API component that can be instantiated and lifecycled the exact same way as the other components are, including OpenStack itself. So think of OpenStack Helm. This significantly reduces the number of APIs, RBAC, and security surface area that we take on as dead every time we add one of these new microservices. So I think that's really huge and worth pointing out. So call to action. The first item, number one on the list, is we really want user feedback. This is the most important. Secondly, help with OpenStack API alignment. Again, these projects were born in the open, but they were not born from the first line of code in the OpenStack Foundation, so there's not necessarily 100% alignment with how all the APIs function. We'd love to hear from people on how to bring that together. Tempest integration, OpenStack requirements work. Again, same thing. These projects were not necessarily born from the first line of code in the OpenStack Foundation, so although we constantly look to OpenStack, not necessarily all of them fit within OpenStack requirements limitations. And of course, we did mention ironic dry dock integration would be really key. Finally, one last point is that a Kubernetes backed by Keystone. So again, this would really drive home the point of one authentication backend for the entire undercloud. There have been several different proof of concepts floating out surrounding this, but really making this a first-class citizen would really bring this together, we feel. So at that point, I'm gonna open it up to questions. And again, there are 3 ways to learn more about this project up on the screen, and I invite everyone to join those.
Hi, I have a question. My name is Sean Kelly. So my understanding is that a lot of this is kind of document-based. So one of my questions is, what kind of tools could Airship provide for when things go wrong? Around syntax validation for the YAMLs and trying to determine debugging solutions.
So I can tackle that one. So one thing we didn't mention in that structure is all the documents are schema-based, right? We have schemas for every possible type of document we have. And that's part of the role of that deckhand tool. It's doing that kind of validations that you just mentioned up front. So Pegleg has a linting mechanism, and deckhand triggers validation when you try to collect the documents for a site. Even when if you saw in the animation that moment where the documents are committed, there's even further validation where we don't just rely on Pegleg or deckhand, but we actually go and ask the different sub-projects, does this look good to you? And that's where something that happens when you commit the document. There's a rendering process within deckhand, and there's an exchange with DryDoc and so forth to ask them, does the documents look fine to you? And so you go ask the question to that entity, that service that has the knowledge to answer the question.
Hi, thanks. 3 questions, actually. Hopefully they'll be brief. So you mentioned you're using this for provisioning active services currently. Can you just generically mention a couple of the use case types that you're supporting with the rendered sites?
Yeah, so maybe a way to describe it that might be helpful for everyone in the room is these are multi-rack environments. They contain many hosts. They have complex networking needs like bonding and VLAN tagging and all of that. We have different SDNs that are in use, and all of those things are being deployed with using this today.
Great, thanks. Second one is for the YAML inputs, have you looked into whether or not they might be generated automatically by some design tool?
I can take a piece of this. Part of that is a gap that we want to close, right? As a tooling set. Internal in AT&T, we have a system called NARAT. It's going to be an inventory system for the physical assets based on an ONAP project called ANAI. That's going to have all our physical inventory, and yes, we're building a tool that's going to read from that physical inventory, and it will convert that to all the YAMLs that depict the physical ingredients of a site, the network configuration on the host IP address assignments, and so forth and so on. So it won't be everything, because that doesn't cover the software layer that we talked about. But most of that software layer should fall under the umbrella of those global settings or type level settings that you do once, and you don't traditionally shouldn't have to go to the site level to change. You might have to, but you don't have to normally.
Thanks, awesome. And last one, once the commit has been done, am I right to think that the commit includes some validation that the behavior you're looking for is actually going to be supported?
Yeah. So yeah, just like Rodolfo mentioned this a little bit back, and that is that there's a couple of phases to the commit. One is a very quick and terse validation that's done on the documents. In other words, if you have layering and other replacement type things going on there and pointers to other things in the documents, and those don't line up, of course you get errors back, but also that when you do a commit, it actually reaches out to each of the backend components. So your bare metal declarations are sent to dry dock to ask it whether it thinks everything is okay. In other words, you have requested a bonding configuration that's completely unobtainable for this particular host, or you have requested to attach it to networks that you haven't defined. Or it's sent to Armada, which validates that I wouldn't be able to run this manifest if I were to actually run as part of the workflow. Our goal here is to fail early and fail quickly to get the user's immediate feedback that there's something wrong with the documents, not submit it to the system and fail 45 minutes into some workflow.
Yeah. Thanks.
So I'm just curious what level of usability you're considering these projects to be at this point.
So I would say that, of course, there's two answers to that question. The first is they're usable in the sense that we are truly using them today to do real deployments. I would say, Rodolfo mentioned this, and we're totally upfront about this, that probably the most major gap about this is that final piece of the end user experience of working with these documents, how to build these documents. Of course, documentation exists, but you still have to get a little bit more deeply into it than we would like. And that's an evolution that we're going to work on, and we're going to make that better. But that would be one of the gaps that we have. These work today. You can use them today. You probably have to get more involved in the document structure than we would like long term, and we hope to close that and make that better with just more tools to make it easier to use.
First of all, thank you very much. It was really insightful. AT&T has done a great job in moving OpenStack forward. I was just curious about how and if this is connected to AIC altogether. If I'm not mistaken, this is for Network Cloud 1.0 related to 5G. Is there any relation between AIC, Network Cloud 1.0?
Effectively the next generation of our AIC platform.
Okay. And is there a migration path between AIC and Network Cloud 1.0 using this model as well? It's a bigger problem for a lot of operators, so my curiosity comes from that, you know.
Yeah.
How do you?
Yeah, TBD.
Okay. Thank you.
No more questions? All right, thank you very much, guys.
Thank you.
Thank you.